just let me move to the right slide. No? Yeah, it works now. Yes, I will just start my second part of lecture, and this will be very brief, and basically it's a design consideration for offshore wind turbines. And we also mention some of design methods and design codes for both bottom-fixed and floating wind turbines. So basically, we design wind turbine to fulfill this functionality, that is basically to generate electricity and in an efficient way. And then we also have to design the structure part of the turbine so that it can survive in the design lifetime, typically 25 years. And this is referring to the ultimate limit state design and the design for the largest possible loads during the lifetime. And also, it's a dynamic machine, so you have to design for the fatigue issues. And I want to point out one important issue, that is as compared to oil and gas platforms. And that is in terms of the consequence of the failure. Usually wind turbines, they are unmanned structures. And when they fail, they do not really pollute. It's basically an economic loss when there's failure in the system. And of course, you have many units in the farm. So if you have a global gross error in the design, then it will be affecting all of the turbines. That is needed to consider. Well, if we look at offshore oil and gas platforms, and they are usually manned as today, and they are rare to large. And then, of course, you will have fatalities and also pollution due to the leakage of the oil and so on. So that the safety consideration is really different, and that is important when you design for the wind turbines. And you have to also have to consider the cost of the structures. And one thing is that you have to follow the design rules to analyze the structure so that you make a good design of the system. The other thing is that you also try to reduce the cost to efficiently use the material in the structure. And then, of course, I will mainly talk about the analysis. So basically the dynamic loads and the response of the wind turbine due to wind and wave excitations simultaneously, and then for the lifetime design. And we start with the blade, and then you have to look at the blade airfoil. And as mentioned by Professor Demetrio, and basically we use a lift to drive the rotation of the blade. And this is much more efficient as we compare to the drag-driven turbines. And as mentioned, so it's important to have a good design of blade cross-section along the blade length, and for different rotation speeds, and in order to get a good power performance. And you have to predict the performance before you actually fabricate and make the turbine. And there's a lot of course, aerodynamic codes that you can use to predict, that I will talk about later in detail. And then you have to look at the loads and the responses to make a structural design of the system. And not only the blades, but also other components in the system, drivetrain, and the tower and the foundation, the support structures. So this, I will later show that the coupling in terms of loads from wind wave and also the induced responses in the wind turbine, that makes it very unique and challenging for analyze wind turbines. And we start with some of the global design consideration, just mentioning floating wind turbines. And of course, you want to have a good hydrostatic stability because you typically have a very large thrust force acting the on the wind turbine. And this gives a big moment on the floating structure. So you have to provide a good hydrostatic stability in order to reduce the inclination angle, typically say around 5 to 7 degrees. Otherwise, you will get less efficiency because the rotor will be inclined. And that is a static consideration. And as I mentioned, thrust force is a very important source of loads on the turbine. And then also you have to consider dynamic behavior of a turbine. If you look at the floating wind turbine, basically we look at the rigid body motion as a whole system. And then also you have vibration issues. That is, for example, blades are very long, slender, and they can be easily bended. And the wind loads are dynamic, and then you have vibration issues. And that we'll talk about this in detail later. So for floating wind turbines, when we consider rigid body motions, we consider basically 3 translational and 3 rotational rigid body motion for the whole system. And then we refer to surge, sway heel, and roll pitch yaw motions. And this is a conversion from the analysis of offshore platforms and ships. Typically, we design, say, relatively large natural periods or low natural frequency, and to avoid any direct excitation from the wave loads. Typical wave load excitation is with a period of 5 to 25 seconds. So you don't want to design a system with a natural period in this region. Otherwise, you will be dynamically amplified with the responses. And then for TLP system, actually we design a more quite a stiff system in heel, in vertical motion, heel, roll, and pitch. And this is giving us more or less 1 to 4 seconds, which is also away, is smaller than the most of the wave period. And for bottom fixed wind turbine, and we also, as mentioned by Professor Dimitri, and most of the first second of the bending modes of the tower or blades, they are excited by the wind loads. We cannot really avoid this. But we design so that it avoids this 1P effect, the rotational effect, and also the relative stiff blades. That we also consider later. And here it's just showing some of the excitation frequencies for these 2 types of wind turbines: spar wind turbine with catenary mooring line, and spar wind turbine with 1 tension leg system. And this is excitation from wave and wind, and as a function of the frequency. So we basically look at short-term response analysis. So we do not look at the very long-term variation wind from days to days. And these are usually referred as long-term analysis. If you are able to do short-term analysis, you can combine them to get long-term responses. Here we refer to the responses, for example, wind turbine in 1 hour time and continuously in time. And so here we have the wind excitation, which is a relatively low frequency. And then we have wave, first order wave frequency. And the corresponding period is about 5 to 20 seconds. You have periodical oscillation of the wave propagations, and then you have wave loads in that oscillation. And when the rotor rotates, you have also this so-called 1P and 2P, 3P effect. Typically, if you have a 3-blade wind turbine, you have 1P effect, and then you have 3P effect. 1P effect is individual blades rotate. For example, go through the shadow area of the tower, and if you have 3 blades, you have 3P effect. These are related to the operation of the turbines. If you operate at different rotation speed, you will have a different excitation frequency. So this is typical ranging for the 5 megawatt wind turbine. And then we have to design the system so that the natural period for rigid body motions is relatively low, so that we avoid, for example, wave excitations and so on. And for the TLP system we design, so they have high natural frequency, which is also away from the first order wave excitation. That is important. So you need to design a system and try to avoid the resonance from the excitation. But in some cases, of course, when the excitation, then you will, with the wind excitation, you will have resonant motions. So the slowly varying motion of the wind turbine in such direction. And if this cannot be avoided, then you have to consider try to increase the damping to reduce the responses. And this can be aerodynamic damping, or it can be other active damping devices you consider in the system. Yes, and for wind turbines, and we have to run analysis for many different wind and wave conditions. As I mentioned, the wind speed change a long time, wave height, wave elevation also change a long time. And then you have to do this analysis for all possible combination during the design lifetime. And also there's different load conditions that are considered for operation of turbines. And normally they operate in normal conditions and with rotating wind turbines. But you have also issues with faults, and then you have to shut down the turbine. And also you may have issues with grid loss, and then also have to shut down turbine. So these are also occur frequently, so that you have to consider during the design of analysis. And as I mentioned, already mentioned that we look at the largest loads in the design lifetime, and we look at the fatigue issues, and in some cases we also look at so-called accidental limit states. And for example, for modeling systems, we normally also consider when there's a failure of one single modeling line, what will happen to the system. The system has to survive also. And this is usually considered for oil and gas platform. But I think typically this should also be considered for wind turbines. And just to say something about the specific floating turbines as their design considerations. And we refer here to semi-submersible, and this is typical submersible wind platform, where you have multiple columns which provide the buoyancy, which are connected by so-called blases. And the water parent area is somewhere there. The red part is showing the part underwater. And then this, it's not very clear, but it's a spar with a heavy ballast at the bottom to achieve the stability. And of course, I mentioned that, for example, if we look at 5 megawatt wind turbine, the maximum mean thrust force at the rated wind speed is about 800 kilonewton, and which gives the moment if we place this at a height of 90 meters. And this overturning moment has to be balanced with stability of the system. And then we also typically design the natural period of heel pitch motion about 20 to 30 seconds. And in that case, we avoid the excitation from the wave, direct excitation from the first order wave loads. And then you need also to consider how to easily fabricate and install wind turbines. So this is also a big issue because you are going to build many units in a farm, 50 to 100 units. So you try to make the foundation structure simple so that for easier fabrication. Try to reduce the welds in the system. And for example, this spar is a very simple structure. But for example, this semi-submersible, you have to do welding at the connection between the brace and the columns, and which is usually costly than just a single spar. So that is also important consideration. If we look at a TOP system, at the moment there's no large size prototype of floating TOP wind turbines. So these are only the concepts. And the basic concept of TOP is that the buoyancy of the floater is larger than the gravity. And so that it gives upward tension in the mooring system. So if we cut all of the tensions, so basically it will flow up and or capsize. So it's important that you have a large tension in the system. So when you have a dynamic loads, then the structure moves, you don't get zero tension, and which leads a slack in the mooring lines. And backwards, you get increased dynamic tension in the mooring line. But that means usually we need to have a larger floater in order to provide a larger buoyancy. But then you get larger wave loads on the floater because the floater is larger. And so this is always an issue that you have to deal with during the design phase. Here we typically look at the natural period in vertical motion duration is less than 4 seconds, for example. Yes, so this is a very important slide on my lecture. I borrowed from Butterfield. And this is, of course, an exaggerated situation from the load point of view for a floating wind turbine. And wind turbine has a very large diameter, so it operates on a very large area where you have turbulent wind field conditions. The wind speeds along the direction of wind direction, they are not uniform and they are not constant. Constant means variation in time. Uniform means the spatial variation is not uniform. And then in waves, you have also irregular waves. You have to consider random seas. And then, of course, they act on the turbine simultaneously. And so that you have to look at the responses simultaneously, looking at the wind loads, wave loads, and also the motion of the structure, because the load has to be added on the displaced position of the structure. And also I mentioned that the blades are relatively long, so there's an issue about alloy elasticity, so that the blades deform dynamically due to loads due to wind turbine loads on the blades, and then you have to evaluate the loads at the deformed position of the blades. And similarly, we also may consider hydrodynamic elasticity, but in many cases, the floater is considered as a relatively rigid structure. So basically, you look at the rigid body motion of the platform. Another point is that then we have to do response analysis, so that to get the response, that means the motion of the platform and also the structural response, deformation of the blade and so on. Another point I want to mention is that you usually have a control which apply in time domain, because it depends on the variation of the speed and so on, or torque. So this that means this analysis is preferably carried out in time domain in order to capture all of these effects. So that is also important issue. Then I will just quickly mention some of the aerodynamic loads, hydrodynamic loads, and then integrate analysis. Then also briefly mention existing softwares that have been developed. I will not go in details very much here, just give you some overview, and we focus very much on this global response analysis. And of course, you have different level of detail or fidelity for aerodynamic analysis. And we do not really use CFD for global response analysis because it's time consuming, and we have to cover different load cases. So basically, we use blade element momentum theory for aerodynamic loads, and this can be considered with the flexibility of the blades and so on, so that also include the alloy elasticity. And in some cases, we also look at, say, the total thrust force acting on the floating wind turbine, and then the induced moment. So basically induce the pitch motion of the platform. So that is just looking at the rigid body motion of the platform. We will mainly focus on this type of analysis. I will mention briefly one-dimensional momentum theory, and then combine with the blade element momentum, elements series, and we get loads on a typical wind turbine. And then we implement some more engineering crashing to the bang method. Yes. So I refer to a book by Martin Hansen from DTU. He wrote the book Aerodynamic Wind Turbine, which is a very excellent book. For those you don't know, so you can read that book. And basically, we started with an ideal actuator disk, which is placed here in the wind field. And as I mentioned, that you will have force acting on the turbine. Oppositely, you will have force acting on the fluid field, which slow down the velocity, wind speed, and then also expand the wave. And based on the conversational momentum, conversational mass, and then also you use Bernoulli equation for the field before the turbine, after turbine. So you get this relationship between the velocity pressure, far field inflow, far field outflow, and outlet, and at the rotor plane. The wind speed will be continuously reducing from inlet and to the outlet, and the pressure will be a drop at the rotor plane where you get the thrust force. So these are the basic assumptions listed here, and from this 1D moment theory, you basically get the power and thrust force as a function of later so-called axial induction factor. Here I just showing some of the results. You can find the derivation from the book. And here we assume that the A is the axial induction factor at the rotor plane. So this basically reduces the wind speed at the rotor plane. And here at the far field, it's more or less 1 minus 2A. And the power, you can get the power coefficient like this, purely called a function of axial induction factor. And then, of course, you take the derivative, which gives 0, and then you reach the Betz limit. And at that time, also, you get the thrust coefficient like this, and which is 8/9. So the thrust force do not reach its maximum when the power reaches maximum. So basically, you relate the power and the thrust to the actual induction factor with this idealized actuator disk. Now, actually, what we have the blades, they are slender structures with airfoil. And then we have to also calculate the loads directly acting on the blade. And these are referring to the lift and the drag force on an airfoil. The airfoil is designed so that velocity on the top passes fast, larger, so flow faster, then you get a low pressure, so you will get a lift force upwards. And then you also have a drag force. So the lift force is basically perpendicular to the inflow velocity, and drag is just along the direction of the flow. And these are the basic lift and drag force, and also get a moment coefficient. And they, of course, will later, you see, depend on the angle attack. And the blades, of course, they are designed so that here I'm showing the lift and drag coefficient as a function of angle attack defined here. It's not very clear, but this green curve is the lift coefficient, force coefficient, and the red curve is the drag coefficient. And of course, if you have relative small angle attack, you will have relative large lift, increase with the angle attack, but at a certain point when you have stall, and then the lift drops, and then you would have relative large drag force. So basically, wind turbine operates in this reading. You utilize the large lift force and the small drag force. Here is also showing some of the features of the lift and drag force coefficients. And then now if we look at an element on the blade, and then we look at the annular element, and consider this as a part of the actual disk. And then we actually relate the actual induction factor, and also because the blade rotates, you have also this rotational tangential induction factor due to rotation. And then with relative inflow wind speed and the rotation speed, you can construct the relative velocity towards the blade. So then you can calculate the angle attack and relate the loads, lift, drag, and then you can decompose the loads in the direction of the wind flow and also along the direction of rotation. So this is just contribution to the thrust force, and this is contribution to the torque, which make the load rotate. And then if you combine this and with also 1D momentum theory for that particular annular element, and then you can derive the actual induction factor on this particular blade run at the particular rotation speed. So you have to do some iterations in order to solve this actuation induction factors. And so basically, in most of the bank code, you run in time, and for each time you do these iterations, get this value. And when you get induction factor, actual and tangential, and then you get the loads also. And these are mainly for relative low induction factor. If you have a large induction factor, for example, if the induction factor reaches 1/2, then you would have reversed flow after the turbine. And then you need some corrections. And this is called growth correction for relative large actual induction factor. I will not go to details. And then also the wake, if you have a change in the wind speed coming to the turbine, and then the wake, you have a dynamic change in the wake. You do not call it statically to get the loads as you normally do for a constant wind speed. So there's a dynamic effect of the wake due to the change of the velocity in the wind. And if you run at a relatively large angle attack, you have the stall effect, and then it depends on the increasing of the angle attack, you have a dynamic effect of the lift and the drag coefficient. So I will not go to these into details, and they are available in Martin Hansen's book. So basically, then from the blade element moment theory, you get the loads along the blades, and also then you can look at the responses if you have a structure model. But I also want to mention that the control part of wind turbine is also important. And we mainly looking at operational control. So that typically for low wind speed, you do generate torque control. So if the wind speed increase, you increase the rotation speed to have the maximum power output. And if you have larger, if you have wind speed larger than the rated value, and then you try to pitch the blade into the wind so that to reduce the loads just, but regulate the power. Here just showing some of the examples for the NREL 5 megawatt reference turbine as a function of the inflow mean wind speed. And these are obtained just running for constant wind speed. And here I'm showing the rotor speed. And as for the small wind speed, you increase the rotor speed when the wind speed increase, and until reach the rated value. And similarly, then you get the power generation. And here, after reach the rated wind speed, you try to pitch the blade into the wind, and so that the power kept constant. And here I'm also showing the thrust force, which is actually reduced. So and then here is the blade tip deformation and so on. So we don't have a problem here, because when we increase the wind speed, then increase the rotation speed. then the charge force also increase. But when we do this for large wind speed, actually we get a reduced charge force. And then for a floating wind turbine, it will give a so-called negative damping effect. Because when the wind speed increases, actually you get less force. So the motion will be further increased. So this has to be also considered in the design control for floating wind turbine. That's particularly important. Yes. So I will not have a break, but I will have a break after the integrated dynamic analysis. So I will continue with the hydrodynamics. And similarly, we may also use CFD for hydrodynamic issues, and in which you can resolve very well the flow details around the structure. But in most cases, for oil and gas platforms or offshore wind turbines, for floating structures, we use the so-called potential flow theory. And later we will discuss more detail. And then also you apply on some empirical crashing due to the viscous effect. And if for slender structures, we can use so-called Morrison element formula, which is only depend on the wave kinematics due to inflow waves. And typically, you can also relate to different wave theory, regular or irregular waves, or linear or nonlinear waves. So that we will discuss later on. So basically, we will talk about these two choices here for global response analysis. And maybe most of you do not know marine technology. And in our field, we mainly more and more rely on numerical methods. And they are more generic to different types of structures, shapes, and so on. And they are more used for design of the structures before you fabricate and operate the structures. And also in traditionally, we also use so-called model testing. And you can imagine that the typical oil and gas platform is very large, and we are not able to build so large turbines for testing purpose only, and we are not able to build a large scale ocean basin. So you have to do this on a model scale, typically 1 to 50, 1 to 100. And in the ocean basin, for example, like this, you can very well control the generation of the wave or current. And this is the important issue. And you generate what you want, for example, the 50-year waves. And in reality, in the ocean, you probably will have to wait for a very long time to get to the extreme wave conditions. So basically, model testing are used to study the hydrodynamic behavior of floating structures. And they are typically modeled as a rigid body structure. So look at the motions of the structure in the waves. That is the main issue. And also, of course, there's more and more monitoring and measurement system on board real platforms. And they are used to give feedback to the numerical models and model test results. So it will be good interaction between these methods. We are mainly talking about numerical method here, a little bit about so-called hybrid model testing for floating wind turbines. And the purpose of analysis is first we needed to describe a good wind wave conditions and considering the stochastic behavior of the wind and wave. And that is important. And as I mentioned, for wind turbine operates on a very large area when it's rotates. And then you have to consider the turbulence model for the wind conditions. And typically, when we look at a single platform, and then we only refer to the wave elevation at a single point. And if you look at a very long structure, for example, floating airport, and then you need to consider variation, spatial variation of the wave condition along the floating structures, floating airport. So basically, we look at the single point wave elevation now for wind turbines. And then we have to estimate the wave loads. Typically, they are just pressure loads on the wet surface of a structure. And then you need to predict, and not only predict when they are fixed, but also predict when they are moving, oscillating in the waves. And then, of course, these loads give the responses. It's typically motion and structural velocity in the system. And that is you need to predict and use for design, for structural design of the system. And of course, I basically refer to dynamic analysis, but of course, basically, as already mentioned, that you have to consider hydrostatic stability first, especially when you have relatively large thrust force due on the wind turbine. And typically here, the hydrostability of spar concept is just rely on the difference in vertical position of the buoyancy center and the gravity center. So basically, you put the gravity center as low as possible to increase this benefit to have a good hydrostatic property. And then if we look at any structure in the waves, and then if the structure is slender, that means if the dimension, cross sectional dimension, like the diameter, is relatively small compared to the wavelength. For example, the ratio is less than 1 to 5, and then we can use the so-called Morrison formula. And this is the expression of the Morrison formula for the force normal to the direction of the elements, and this is the force per unit length. And they are only rely on the vertical acceleration, vertical particle acceleration due to the waves, and the velocity due to the waves. They are pre-known before you put the structure. So they are only referring to the incident waves, not to the assuming that there's no influence of the presence of the structure. This force we refer to inertial force, and this we refer to drag force. As you can see that inertial force is a linear function with respect to acceleration, while drag force is a quadratic term with respect to velocity. So that means in relatively large waves, you would have relatively large contribution of this term. Otherwise, this force is dominating. So that is important to understand, because there's different contribution for small waves and large waves. And if we consider structures moving, then you consider the motion of the structure in terms of velocity, acceleration, in a relative term, and then get the Morrison force for that case. Here I just show you some of the famous picture here, and that is looking at a board fixed cylinder under the wave, and look at the total wave loads on the cylinder. And assuming this is, of course, the slender structure. And here is also referring to the ratio to the diameter. So when this is larger, you have more like extreme waves. And then if we also refer to the diameter to the wavelength. And if this is small, then it's more like slender structure. And if this is large, then the drag is more dominating. So this is a very important plot, so that you can check for your structure for different wave conditions. And of course, the coefficient in the Morrison formula, eddy mass coefficient and drag coefficient, they rely on the flow conditions, typically found due to Reynolds number and Kc numbers. So there's a lot of study in offshore industry for getting these coefficients. And this is showing the drag coefficient as a function of the Reynolds number. You also see a particular drop in certain Reynolds number for the drag coefficient. There's also handbooks that you can get these coefficients for different type of structures. And the Morse formula can be used typically for slender wind turbines with slender support structure. For example, like monopile, if the diameter is not so large, and then jacket element, or even the spar floating wind turbine. But also you have to check with the relative wavelengths in order to use it. Now, if we have relatively large volume structure, for example, like ships and or semi-submersible, and then when you have the structure in the wave, and then the structure also moves, and typically we have to separate as two problems. One thing is so-called the diffraction problem. That is when you fix the structure, then you have incoming wave, then you look at the loads acting on the structure. And then another problem is the radiation problem. That is to say, you let the structure oscillate in the water, then it will generate wave, outgoing wave, and then you have also wave loads on the structure. Then you can combine them to get the total wave loads on the floating structure in waves. So, and here, of course, you have to assume it's linear combination of these two problems. And what we get from the diffraction problem is the so-called excitation force. And then from the radiation problem, you get added mass and damping. Of course, also get hydrostatic restoring force. These forces are motion dependent. So you have larger motion, the magnitude loads are larger. And also important thing that we do not consider any viscous effect when we use linear potential flow theory. So you have to additionally add this viscous drag force along the structure of the platform, if this is important. And that is the first order wave loads, and we saw typically we use the bundle element method and the numerical method to solve any wave loads for any type of floating structures, and in a linear sense. And then, of course, usually we also enter into second order effects. They are important wave loads for mound structure, where you have relatively large natural period. The magnitude of the second order wave loads, the absolute magnitude, they are relatively small as compared to the first order, but they might excite the resonant motion of the platform. So that is also important to get. And if we consider regular waves with two frequencies, and then you may have different frequency load components and some frequency load components. And these low frequency components, as I mentioned, will give excitation for the resonant motion of the mountain structures. I will not go to details, and they are very well developed commercial software to predict wave loads on floating structures. And this linear or potential flow theory can be used for relatively large volume structures like gravity-based foundations or semi-submersible or TLP structures. In some cases, when the column, the diameter column is not very large, we can even use a Morse formula for these structures. But of course, there's potential flow theory give universally valid for any type of structure. It's also valid for slender structures. So when you get all of the loads, the wind turbine loads acting on the blades, and hydrodynamic loads on the floater, and I also forgot to mention that for marine lines, you also use Morse formula to get the loads on the marine line. And then all the loads are acting in the same system, and then you have to do the response analysis. And what is important to notice is that the wind turbine loads basically come from the lift and drag, which is a quadratic term with respect to the velocity. So basically, they are nonlinear forces with respect to velocity. So you have to do this in a way, in a coupled sense, so that you have to solve the motion, get the loads and then solve the motion, and then do iteration to predict the loads at a deformed place and so on. So these are important and are mentioned preferably to perform in the time domain, and when you consider also automatic control of the wind turbine. And if you have a model and method ready, then you can do this for different type of wind and wave conditions, and then you predict extreme and fatigue loads and load effects. So that is important. Another point I want to mention is that most of the hydrodynamic loads, they predict using frequency domain method. That is predicting the loads for on the structure in regular wave condition for a given omega. And this is possible to convert in the time domain. And this is equation motion, actually for the floater under the wave loads, excitation loads, which is independent of the motion. And then you have this inertial effect. And the other type of three components, they are the wave loads, motion-dependent wave loads. And then it's possible to convert into time domain. And these loads at the mass and the potential damping coefficient, they are frequency dependent. And when you convert into time domain, you end up with so-called convolution term, and with respect to velocity term of the motion of the structure. So when you solve the motion for time t, then you have to do this convolution for the time before t, and to see this effect. And this appears a radiation force in this. And this is only for the wave loads. And then if you have a structure on wind turbine and blades, then you can add upon the other type of loads and to the whole system. Here we only refer to the rigid body motion, 6-degree rigid body motion of the floater. Yeah, okay, here there's some overlaps here. But here I just want to show some of the examples for more on the structure, how the motion behaves in wind and wave. And this is a general floating structure. So typically you would have mean force acting on the structure. For example, if you have a wind turbine, you have a mean thrust force. And this displays the floating structure to a new mean position. And because the molecules are relatively soft, so they give a small restoring effect. And then on that, you will have dynamic loads when you have oscillation along the mean position. You have oscillation due to first order wave loads. We refer to wave frequency oscillation. And then you have resonant motions and due to the second order wave loads, and which is typically slowly varying. So that it's possible to decompose it into first order wave loads, and which typically due to the without consideration in Morris system, and then also possibly to add the second slowly varying part, where you have the second order or wind loads, and then the strong influence of the Morris system. The Morris system is basically designed to constrain the motion of the platform, but they are not like a fixed structure. So you allow the wave frequency motion under the first order wave loads. You see you cannot restrict that motion. It's basically that the first order wave loads are very large. So if we want to restrict this motion, then all of the loads will transmit it to the support structure. For example, like a bottom fixed structure, you would have wave loads, first order waves on the structure, which converted into the loads in the support structure. Well, here we allow the wave-induced rigid body motions, and then mainly restrict the mean offset and the slowly varying motions. And here just showing some of the basic effect of Morris system on motions. And of course, you have to consider stiffness effect, the restoring effect. If you don't have Morris system, the structure will drift away and horizontally. And then when the water depths increase, and then you also need to consider inertial effect and damping effect. Inertial effect mainly means if the mooring system moves, and then you also have the inertial force on the mooring lines, which will add on to the motion of the platform at the fair lead. And you have also drag force on the mooring lines, which bring also the damping force with respect to the motion of the platform. Yes, and since 2005, there have been a lot of development of software for analyzing offshore bottom fixed or floating wind turbines. And this IEA OC3 to OC5 benchmark study is basically the code to code comparison, and now they enter into code experiment comparison. So it's basically coordinated by NREL from the US, and they have gone through different phases for considering different foundations. And I will not go into details, but if you Google, you can find a lot of reports, annual phase reports for different periods. And this is showing the codes that is compared in this benchmark study. First is the code from NREL. It's open source code, and similar reference Aerodynamics. It's a code developed at the NTNU. Basically, we use similar reference for hydrodynamic and marine analysis, and Aerodynamics from NREL, which is open code for aerodynamic analysis. How2 is from DTU, and basically these three are major codes, and Blade is more commercial codes from Gary Hansen. Here also showing some of features in terms of aerodynamics, hydrodynamics, structural dynamics, control, and mooring system. And more or less they are using similar aerodynamics. There are some slight difference in hydrodynamics and mooring system formulations. I will not go through into details. I also found in the report. I just mention briefly how we constructed this code in similar reference Aerodynamics for aerodynamic analysis of a typical bottom fixed or floating wind turbine. So basically, SIMO is regarding the wave loads on the platform, and which considered as a rigid body. And then reference code that is a finite element based, nonlinear finite element based code that you can look at loads on slender structure like mooring lines, power cable, and so on. And then we use Aerodynamics, where also combined with the turbine sim, the simulation of turbulent wind field. And then all of the loads are predicted from SIMO, Aerodynamics reference. They are converted into the same structure model in reference. And then you solve these motion equations for rigid body motion and deformation of structures purely in reference. So this is a typical structure of software. And here is just showing some of the modeling and features in terms of structure and external loads. And you decompose the structure for slender elements using, say, typically beam elements, for blades, tower, mooring lines, and then you consider a hull as a rigid body. You get hydrodynamic loads on integrated hydrodynamic loads on the rigid body, and then you get loads from this code and solve the equation of motion on the wind and wave excitation in time domain. And then I will just I will just want to stop here before I give some examples of the analysis for different type of structures. Any other questions up to now? Yes? Yeah.
My name is Flavio from Ghana. I want to know, are there any externalities associated with wind turbines?
Sorry?
I said, I want to know, are there any externalities associated with wind technology?
Yeah, you mean the wind turbine?
Yeah,
here we are looking at the wind turbine responses motion or deformation of structure under the wind and the wave excitations. So basically, you have to look at that in order to design the structure, dimensioning the structure in the blades or the support structures.
Okay. Now, so my second question is, you know, for wind technology, we have these elements that they use, the real earth elements. Now, I had a course on impact and externalities of all the renewable energies, and we came to understand that for the wind turbines and also the generators, there are some real elements that they use when they are producing the generators and the wind turbines. And now research is saying that it's only China who are like they have the resource. So I want to know what is the future of wind technology if this real element, you know, they diminish like fossil fuels. Now we are saying that there is the depletion of fossil fuels. We are migrating into renewable. So what is the case for wind energy if this element they diminish in the near future?
Yeah, I think as long as we have the Earth and the globe, and there will be wind, and as long as we have wind turbine, you can generate wind electricity. The problem here is that we design the structure so they survive for the design life, maybe about 25 years. And after 25 years of use, you will get a lot of damage due to fatigue. Then you have to replace them or reuse some parts of this. And this is also related to the cost of the system. But for resources, and they rely on the resources itself. There's a limited resource. I don't think there will be a limitation of wind resources in the future. Yeah.
Really, but the same thing applies to fossil fuels. Like they are so big, like a reserve is much, but we are saying that it's depleting, let's go to renewable. The case still applies to wind. That element, there are two elements, diprosium and I think another one is niprosium. So
do you think that we will have no wind in the future sometime? No, this circulation of the ocean and land, you will have wind certainly. Yeah.
Oh, for me, I'm thinking is like we just talk about the positive side, and we don't look at the negative side. Like yeah.
Certainly there will be a lot of negative side. For example, for offshore wind turbine, you occupy the large area of offshore space, so there might be other use of offshore spaces that you have to compromise.
So in your opinion, you are saying that this raw element will not have negative impact on wind technology in the near future?
You mean the components in the system? Yeah, there's some raw material in the generator, for example.
Sure.
That of course, yeah,
that
will limit the wide use of the wind turbine. Yeah, I'm not an expert on this. So I cannot really comment on that. Yeah,
all right.
But there's a booming or increasing use of wind power, and at the moment we are not used a lot. In fact, especially offshore. Yeah.
All right. Thank you.
Yeah. Any other questions?
Hi, Professor. What kind of turbine control has been used today? And if are there difference to onshore or offshore generator, like induction or synchronous, when you using offshore?
Yes, I'm not familiar with the generator control, but overall, we use the generator torque control for low wind speed and blade control, pitch control for high wind speed. And they are similar, very similar for bottom-fixed offshore wind turbine and onshore wind turbine. But when we looking at the floating wind turbine, as I mentioned, you have to dealing with this negative damping issue. So you have to tune the pitch blade pitch controller so that it do not excite the pitch resonant motion of the structure. Otherwise, you will get large motion and responses. Yes. Any other questions? If not, I can just go on, because we have many slides left. Yes, then I just give some examples of analysis of different type of wind turbine, jacket, spar, and then also do some comparative study of different type of floating wind turbines. Yes, we have done a study for a jacket wind turbine in water depth of 70 meters. And we refer to the NREL 5 megawatt wind turbine. And then this jacket is, the total height is 90 meters and the water depth is 70 meters. We are interested in the dynamic feature of the system on the wind and wave excitations. Here I just give some examples. And of course, the first global bending mode is due to the power and the foundation and also blade. Then you would have, which is at the natural period of 3 seconds. And then you would have the second bending modes, and where you have large contributions from the foundations, jacket structure, which typically have a natural period about 0.5 seconds. And here we are just showing some of the comparison. If we just apply wind loads and just apply wave loads and then combine the wind and wave loads, how the response looks like. And these are showing the spatial density function of the global bending moment at this location at the sea bottom, this fall after bending moment. In condition with the mean wind speed 50 meters per second, HS 4 meters, TP 8 seconds. They are referred to the wave conditions. So basically it's the turbulent wind and irregular wave that we are considering. Here you can see that they are slowly varying, mainly due to the wind loads excitation, but they are not dynamic, it's called a static response. And then we will have a wave-induced, which is also called a static. Then we also have this first bending mode. So they are dynamically excited responses. And further, we actually have also the second order, second bending modes excited. They are basically due to wind loads. And here, wave loads do not excite any dynamics. It's called static loads. So if we do this for different wind and wave conditions, and then we can look at the, say, the fatigue damage in the jacket foundation. Because they are weld structures, and usually you have initial cracks there, and then the fatigue becomes a very important design issue. Here I'm just showing some of the comparison for different joints at the support structure, in the support structure. And then also showing some of the difference if we only look at the wind loads, the blue, and then look at the wave loads, yellow, and then look at the integration effect. Because the typical loads in the jacket elements, like blades, the actual force and bending moment, as I mentioned, they have typical spectrum like this. So these are, we refer to a wider band spectrum. And for fatigue, then you have to use the rainfall cycle counting method. And so you have to look at the total stress time series and then do fatigue assessment. And these are the contributions for different locations. If we look at spar floating wind turbines, and there's also mooring line, it's not really visible, and the displacement is about 8,000 tons, and which is for a 5 megawatt turbine. And the draft is about 120 meters. So it's a very deep structure. And here we show some of the, say, the decay tests using numerical method. And then you can also get, say, we apply, of course, the distributed drag force along the spar element. Then you can also estimate the linear or quadratic damping coefficient with respect to different motion modes. And here showing some of the response, say at this is the pitch motion response, and this is the marine line tension response, and for a given wind and wave conditions. And you can see that the pitch resonant responses are excited by the wind load, and then you have also wave-induced motions. They are not resonant motion because the natural frequency is around here. And then if you look at marine line tension, you still have this pitch-induced resonant motion induced contribution, and then you also have large actually influence due to the wave loads and induced motions. So these are just some slides give you an idea about how the system behaves in wind and wave. And then we also have done some studies for different type of floating wind turbines, spar, semi, TLP, and referring to the same wind turbine, annual 5 megawatt wind turbine. And then we compare the motion, pitch motion for different conditions. These are operational conditions with mean wind speed at a rated wind speed, and then parked condition. Parked means that I forgot to mention that the wind turbine will not operate at a certain point wind speed. And that is typically 25 meters per second. And then you park the turbine, either idling or fix the turbine without rotation. And then you turn the blade into the wind to reduce the drag force on the turbine. Here again showing the typical pitch resonant motion due to wind loads, and here is not visible wave loads. And then also we see that the green curve is referring to the TLP, and this is amplified 1,000 times. So the TLP system has a relative stiff structure. You don't have a lot of pitch motions and so on. So this is one particular advantage of the TLP system. But you have to design the tandem so that it can take the wave and the wind loads on the platform. And then from Junkerman and Mata, they also studied the other type of floating wind turbines. In particular, they include this barge floating wind turbine. And then, of course, the wave loads on the barge is very large and then induce large motions. So they compare the responses, different responses from a bending blade root bending moment and also the tower-based bending moment as compared to the land-based turbines. And of course, you also see that there's a big increase for the barge type of wind turbine. So it's not a good idea to use barge or ship type floating wind turbine. Basically, its wave loads are too large, and then you have large motion, wave-induced motions. And in May, in the Netherlands, they have done a lot of model testing of floating wind turbines, and also have been used to validate numerical models. And here are just some early days of comparison. And here is a model test, a semi-submersible with a flexible tower and then the blades. And these blades have to be designed so that it matches the thrust force for the given wind speed at the model scale. You cannot really geometrically downscale the rotor, and where you get relatively low Reynolds number, do not get the satisfactory lift and drag coefficient. And here then also compare with the numerical estimation. At that time, I think the fast code do not consider second order wave loads, and then some difference in terms of second order wave motions. But I think now they include these features. And in Statoil, they have, as I mentioned, they have been running the hard wind demo since 2009, and then they also have measurement of the system. And then they compare also some simulations, and here also showing some of the bending moments and fore aft and side to side bending moment. It's not very clear shown here, but with simulation and with measurements. Yes, so these are just a quick description about the thermodynamic feature of offshore bottom-fixed wind turbines and floating wind turbines. Do you have any questions? This is very short. If not, then just continue. And I still have two parts left. One is on vertical axis wind turbines. The other part is more or less highlights of research work we are doing at NTU. I try to finish within, say, 45 minutes. Yeah. So we get proper time for lunch. And here I will just briefly mention vertical axis wind turbine and as compared to horizontal axis wind turbine, and basically look at the aerodynamics and then also integrated analysis. We have the same software feature for hydrodynamic part of the vertical axis wind turbine, and then do some comparison between the floating vertical axis wind turbine and the horizontal axis wind turbine. And we mainly refer to horizontal axis wind turbine this type, and then vertical axis wind turbine is direct turbine, and then H type with the straight blade vertical axis wind turbine. And they, of course, you basically use also the lift force as the main driving force for electrical generation. And here we're showing the basic power coefficient and for a given tip speed ratio, and for normal three-bladed turbine, and also for direct turbine. And basically, you get less power coefficient with the vertical axis wind turbine. And another issue is that the turbine variation power is also very large. And later we will show that when the turbine, vertical axis wind turbine rotates, the angle attack is changed from 0 to 360 degrees. So you have a big variation in terms of lift and drag force, and then the bigger variation in thrust and the power. And then we consider similar support structures for bottom-fixed and floating ones. And here also showing the Betz limit and the typical operation maximum power coefficient for other type of turbines. At the moment, there's no commercial or even prototype, large-scale prototype of vertical axis wind turbine. And there was a study on this so-called deeper wind, and this is a quite unique turbine. It's a vertical axis wind turbine, but the floater actually also rotates. Not only the tower and the floater actually rotate, and the generator is put on the bottom of the floater. And then there's also other type of proposals of different vertical axis wind turbines, and they are just on the conceptual level. So if we look at the turbine advantage first, and they are independent of wind direction. So you operate at any direction of wind at the same condition. And then, of course, there's might be an advantage to use for floating application, because you can lower the center of gravity by lower the generator, put the generator at the platform level. And it might be easier to install or operate. And, but the main issue is that you have relatively low power efficiency. And also you have large variation in terms of loads. And then you have bigger fatigue problems. I will show some of the issues here later. So there were 2 PhD students working on this in our group. And they already finished. And their main idea is to develop numeric codes that can be used for analyzing floating voltaic acid wind turbine. It can be also applied to bottom-fixed turbine. So it's following the same idea for horizontal acid wind turbine. You have to look at the aerodynamic loads and also considering, say, flexible blades. And it's not easy to control the blade pitch angle for voltaic acid wind turbine, especially for this dialless turbine. So typically you have a fixed pitch angle. If you have a vertical, straight H-type blade rotor, then it's possible to adjust the blade pitch angle when it's rotated. So the idea is to look at the loads and the responses and then compare with the horizontal acid turbines. And there are not so many codes that are being developed. There are some. And I will just mainly mention the code we developed. And basically using, later I will mention this double string tube aerodynamic code or actuated cylinder code. And in DTU, they also have integrated this into Hot 2 for voltaic acid wind turbine. So the purpose is to develop a fully coupled method for analysis of the floating voltaic acid wind turbine. Basically, we use quite similar aerodynamic models and more or less same hydrodynamic model as we can compare to other type of codes. There's a bigger variety of different methods for aerodynamics or voltaic acid wind turbine. And you can go through to the CFD method as mentioned. But I mainly will talk about double multiple string tube method, and which combines the blade element method and moment theory. And then the actuated cylinder flow models. The basic difference is that the DMS, and they only calculate actual induction factor, while the AC model will calculate both actual and the cross-flow induction factor. Later we will see also that you not only get a force along the wind direction, but also side-to-side force. So that is also particular problem for voltaic acid wind turbine. Here showing some of the comparison of the force acting on the turbine and for different azimuth angle when the blade rotates. And comparing with the DMS, AC, and with other more advanced codes. The DMS model is that if we look at the Darius turbine, and then if we look at from the top, you get this cylindrical element, or this part, and then you consider main strip and along this direction, that is the main wind direction, and then you use actually two actuated discs to present the aerodynamic force along this one particular string tube. And then if you combine all those in, and for all the blade elements, then you can get the loads distributions. I will not go through details, and it's basically uses blade element theory and ground momentum theory. It's very similar to the actuated disc model for the horizontal acid wind turbine. Well, the actuated cylinder model is that you look at the whole, it's the same strip, and then you look at the actual cylinder to replace. And then you have to solve this to derive the induced velocity using the continuity equation and Euler equations. And this is assuming the potential flow. And when this induced velocity is solved, then you can find the loads on the cylinder. And then you do also the integration along the this one from 0 to 300 degrees of oscillation to get both actual and cross-flow loads. I will not go into details, but I have the reference to two of the PhD theses, and then you can look at in detail. Here I just compare some of the test results from Sandia lab with 5-meter direct rotor, and another is 17-meter direct rotor. Here we only compare the power coefficient for different tip speed ratio. And here you see that they more or less, these dots are the experimental data, and these two methods more or less follow the same trend. And the AC model slightly give slightly better results. So that is the overall behavior of these two methods. And then now we apply the method, develop a method to the floating turbines. And we use the same structure for structural hydrodynamic analysis and structural analysis. And basically change the aerodynamics so that we can use for vertical axis wind turbines. And it's also possible to consider flexibility in the blades in this case. So these are more referring to the software that we used. As I mentioned, this software, LightPhrase, is used for modeling slender structures and to look at loads on the slender structures. Simo is for hydrodynamic parts and on rigid bodies. And then we also use the same wind generation for horizontal axis wind turbine. And then we use either AC or DMS model for aerodynamic part. So then you can do an integration, integrated dynamic response analysis. Another point is that, as I mentioned, that you don't have the possibility to pitch the blade to control. And this is a particular challenge because for horizontal axis wind turbine, we pitch blade for high wind speed so they can regulate the power. And here we actually try to use generated torque control so that you have to measure the wind speed coming to the rotor and also measure the rotor, then identify the operational region for the particular turbine. And then the controller is trying to minimize the difference between the actual rotation speed and the reference value for that particular operation mode. And this is basically using a PID controller to regulate. And here we plot the idealized operational condition, rotation speed for different wind speed, and in this curve. And there's two different control strategies for high wind speed. One is so that you keep the constant rotation speed, and then you get a larger power. And another one is just to try to give the constant power, and then you have to reduce the rotation speed for high wind speed. So basically, this we look at this improved controller when we compare with other floating wind turbines. Now we look at some comparison we have done. First is code-to-code comparison. Basically, we look at the code we develop and also compare with HOG2, and for bottom fixed one and floating ones. Here we just showing some examples about for low wind speed operation, they are steady operation. And here I'm showing some of the results in terms of torque and the thrust force. And you can see there's a big variation. And these are so-called the two-peak variation because the blade will experience different angle attack when it rotates. So that is giving a big variation in all of the load components. It's also appearing in the power output. And basically, the AC model and the DMS model, they give relatively similar results. And then we look at, say, turbulent wind and irregular wave conditions, and then look at, for example, the tower base bending moment for after bending moment, and how the response looks like. And I do not explain other parts, but just to mention this 2P response. Since you have, here we consider 2 blades turbine, and there we have very strong variation due to the rotation of the blade. And this even happens in the wind, constant and uniform wind, because you cannot really change this. The angle attack is vary from 0 to 300 degrees. And then we talk about the 2 other cases we studied, that is try to increase the number of blades to reduce this 2P effect. And then we also look at the comparison between a horizontal acid wind turbine and the vertical acid wind turbine, more on response point of view. And here we just define some of load cases with increasing wind speed and the corresponding increasing wave conditions. And later we show these results for these cases. And now we look at the first case. And of course, you have to redesign the blade so that we actually end up with the same output of power, that is 5 megawatts. And here we design the blades to basically redesign the cord length of the blade so that you achieve the same generator power. And then we use improved control strategy we just mentioned. Here we look at some of the results, and in terms of power, and here is the mean value of the power. So they basically give the same mean value. And for the, when you reach the relative wind speed, it's 5 megawatts. And then you also look at the variation in terms of standard deviation of the power, if you look at the time series of power. And you can see that there's a higher, this red is for 2 blade case. Then you have 3, 4 blade case. And if you increase the number of blades, then you can actually reduce a bit of the variation of the power. So they reduce the 2P effect. And here is showing the time series power. And you really see that there's a bigger variation in the power for vertical acid wind turbine. And now if we look at further the structural response and just look at the tower base bending moment and or say the thrust force acting on the platform, on the wind turbine, you have also seen that there are bigger variation for the 2 blade case, and then you have reduced variation when you increase the number of blades. And here I'm showing some of the spectrum for the load case 7, and here you can see that even it is in turbulent wind and irregular waves, and you have strong variation due to 2P effect. These are more like deterministic variation effect. And then you increase the loads, and then you reduce. Of course, you will not get 2P effect when you have 3 blades. Then you have also 3P response. Then it's also reduced. So it will be beneficial to increase the blade number from 2 to 3 and 4. Yes, and then if we look at the further motion, they do not really influence a lot, and basically they are governed by wave-induced motions. And then the marine line tension, there are some reduction in the dynamics, but not so much. So basically, if we increase the number of blades, then we can reduce a bit the aerodynamic loads due to 2P effect. And then the global behavior, for example, mean value of the power is not effect at all. Now we can also further go to the comparison between horizontal acid wind turbine and vertical acid wind turbine for floating spar application. So basically, we look at the same floater, and two turbines with the same generated power, rated power. And we actually also use the same mooring system. There's a particular design also called the delta mooring system. And this is mainly try to increase yaw stiffness. Because you also have yaw moment on the wind turbine. That is also needed to be balanced with the restoring from the mooring system. And then we also look at now the power performance, and these are the mean value of the power performance. And of course, we look at for different load cases we just explained before. And the mean values, they are more or less the same. And but for variation of power, certainly the vertical acid wind turbine, you have relatively large variations. And that is also a particular challenge. And if we look at the loads, the thrust force, there's even larger variation for the vertical acid wind turbine. But just to remember that here we consider two-blade vertical acid wind turbine. But if we increase the number of blades to 3 to 4, then you also are able to reduce the variation in the dynamics of the system. And then you have also the platform motions, and which important to see that you also have a bigger mean contribution for the vertical acid wind turbine, because you have a larger torque applying on the vertical acid wind turbine, which gives the mean larger yaw motion. And if we further look at the spectrum of the tower-based bending moment, fore aft means along the wind direction, and side to side is perpendicular to the wind direction. And you can see that this 2P effect is quite significant here. And otherwise, waveframes motion or slowly varying motion, they are more or less similar. But if you further look at the side-to-side bending moment, you do not see actually any response for the horizontal acid wind turbine, because there's a very small side-to-side excitation from the wind turbine. Well, you also you get actually quite large excitations for the vertical acid wind turbine. So that is, of course, also a challenge for designing the, for example, mooring system. And then if we look at other components like mooring line tensions, and basically we can conclude that the current design of this vertical acid wind turbine has a larger responses as compared to horizontal acid wind turbine. But if you try to increase the number of blades, you may get more or less similar responses. So this is just about a brief about the work we have done on vertical acid wind turbine. Do you have any question? I just stop now before I give the last part of my presentation. Any question?
Hello, I'm Kishore from India. I need your opinion on vertical axis wind turbines. Nowadays, in some countries, they are placing vertical axis wind turbines in between the highways while moving. So, how advantageous are they? I know little bit of it.
I think these are very small scale turbines. And here we are mainly comparing the large scale turbines and for electric generation and for grid connection. So I don't have any opinion about this. But as I mentioned, we mainly look at large scale turbines, and there's a potential this benefit of having a lower center of gravity for the vertical acid wind turbine, because you can place the generator at the platform level. And when you get a larger and larger horizontal acid wind turbine, and then the nacelle has to be placed at a very high level, and then you need to have a very large floater to get the hydrostatic behavior. And then if you are able to lower center of gravity, it will be a beneficial. Then one direction for vertical acid wind turbine is that you can lower the center of gravity. Yeah. Yes.
Hello, my name is Ian. I have a question about why the hill all the data you show us is about the hill. Why you study the hill, not all other kinds the vent like Savonius? Because Savonius is stronger than the hill. Why the hill?
Yes, you mean the vertical acid wind turbine? As I mentioned, that direct turbine you basically use lift and the driving force, while Savonius turbine you use drag, and then of course the efficiency is much less. So for the drag-driven turbine, and this do not explain here, but it's showing here. So the power coefficient is 0.1, while here we have 0.35 and 0.5. So for large scale turbine, I don't think we will use this drag type of turbine. Yeah.
Hello, my name is Heitor from Brazil. Do you have any cost study related to increasing the number of blades in this vertical axis that you showed from 2 to 4? How this would impact the total cost of the turbine?
No, we haven't done any study about the cost evaluation of the vertical acid wind turbine, because these are more like a conceptual study. So we even not sizing the generator and so on. So, but it's possible to roughly estimate because we have the design of the blades profile and the material and so on. So it's, yeah, but we haven't done this. Yeah. So if there are no further questions, then I just give my last part of presentation. It has been a very long morning for all of us. So I will be very quick and brief for the last part and just highlight some of the study we have done. And this is mainly done by the PhD and the postdoctors in our group. And I also have other colleagues as professors. This group is mainly led by Professor Togemon, and he's not able to give a presentation here. And I just select some of the results we have been working on since 2009. So it has more or less 10 years of work. And basically, we starting from the hydrodynamic parts, marine aspects, and then we also look at the different modeling aspects. For example, using Morrison potential flow theory for hydrodynamic analysis of, for example, the floating wind float concept. Another issue is that we also look at the nonlinear wave effects. For example, this TLP raining effects. And usually they are due to high order wave loads. Typically, these are not considered for structural design of normal structures, but they are unique for TLP type of structures, where you have relative high natural period for pitch and pitch motion of structure. And another part is that we also look at how the structural response to the faults in the system, in wind turbine system. And these can be faults in the gravity system and or, for example, the grid loss and so on. And this can also be related to the failure in the pitch actuator for the blade. For example, they usually use hydraulic pitch actuator for each blade. They can be individually controlled. But if there is a failure in the system, you cannot pitch the blade. And then how the response will increase and how we can identify this event, then try to shut down the turbine to bring into a safe condition. So here is just showing some of the analysis we have done, and here showing the tower bending moment and as a function of time and during normal operation, and then when this fault occurs, and here is referring to one blade cannot be pitched and during this operation. And then you would have increasing dynamics in this tower bending moment. And if we will identify this event, then we try to shut down by pitching the other two blades so that you get a drag, so that slow down the rotation, and then you bring to a safe non-operational condition where you have small loads. So this type of analysis will also be running this because this is required for design analysis. Another part is that we also look at the drive chain response, in particular response in the gearbox, in the gear tooth, and how they increase. For example, if we place a wind turbine on floater as compared to a bottom-faced ones. So, and then usually we have to use so-called decoupled local and global and local response analysis. So we use, for example, blade moment theory and hydrodynamic analysis to get the low-speed drafts, the loads in the low-speed draft. And then you have typically a very detailed gearbox model, and then impose the low-speed shaft loads on the model. And then also for floating structure, we can also consider the motion-induced inertial loads in the gearbox. Here it's not very clear shown, but we are able to predict the loads, the pressure between the teeth of the gears, and then you can do also, say, structure analysis or fatigue design of the gears. And in some places in cold places with ice-covered areas, and then there's also particular interest to look at the ice loads on the turbines. And here we look at mainly the level ice. So it's the ice sheet on the surface of the water. And when you have ice, you typically don't have waves. So it's when here we basically look at the wind and the ice-induced loads in this case. And then you have to look at the ice breaking mechanism and predict the loads at the circumference of the support structure. Because these are very dynamic, also then you excite the first or second bending modes of those systems. And another study we have also done is try to use a hydraulic system to replace the gearbox drive chain, and then you can bring down the motor generator to the platform level, and to reduce the center of gravity. And we also make a detailed model of the hydraulic systems in order to couple this system into the global analysis. And of course, we are interested in different types of turbines, different floaters, and for different size of turbines. So we are basically looking at 5 megawatt aerial and 10 megawatt TTU turbine, and also try to see the difference in terms of floaters for different size of turbines. So, as I also mentioned, we look at vertical acid wind turbine as a study also. And for jacket wind turbines, and we are particularly interested in fatigue loads in the joints, welded joints in the jacket. And also we try to use, say, inspection planning to increase the safety level when we look at the system. So there's, normally, of course, there's not so many jacket wind turbines yet, but in offshore area, for oil and gas industry, there's a lot of jacket structures. And then they usually do inspection of the cracks in the joints regularly, for example, 4 or 5 years, and then to see whether you identify any cracks and compare with the prediction you made actually before you do the design of jackets, and to see the differences. And this actually tries to quantify the uncertainty that at the design stage and then after certain year operation for fatigue assessment. And as I mentioned, that we look at the drivetrain and look at a very detailed model of the gearbox and the contact between the teeth. And one important aspect is that what will be the increased load in the gearbox if we put the same turbine on the floater as compared to a land-based? Because the floating wind turbine, you have large, rigid body motions. So you will have increased loads in the wind turbine and also in the gearbox. So it's not very clear shown here, but this is like to show the increased percentage in terms of, for example, the actual force. So there's like 100% increase in the actual force on a floater as compared to land-based. And then also there's a bending moment increase and so on. So basically we suggest that you have to look at explicitly the loads in the drivetrain and by doing analysis and then design the gearbox. And also we have, together with SINTEF Ocean, which is a research institute mainly working on marine structures, and they have a lab that do model testing. And we also do model testing for example, this is a case of foundation, monopile foundation, but we consider as a flexible structure. So the first eigenmode are captured in the test. And then look at the extreme wave loads on the foundations and so on. I want to highlight one of the study here that is using so-called hybrid model testing. And the issue is that we cannot really have the same scaling law for floater and for wind turbine loads. Basically, we have to use fluid scaling law for hydrodynamics, and then we have to use Reynolds scaling law. And they cannot be certified at the same time. And basically, we have relatively small Reynolds number at the model scale. So here, what we do is that we use the physical scaled model for the floater, and then we generate the wave in the ocean basin. And then the wave loads are physically applied on the floater. And then the wind loads, actually, we use a numerical model, and also together with the wind field generation. So you generate the wind loads using numerical model. Then you have to use an actuator to apply on the structure. Here, actually, we have 6 cables which connected to the a motor that give actually the simultaneous load, which is basically it's the integrated load that you can apply on the wind turbine. So in this way, you can study the integrated coupling effect due to the simultaneous wind and the wave loads. Of course, you have to be sure that the numerical model are correct, and then of course it's meaningful to use in the system with hybrid testing. So here is just mentioning some of the advantage of hybrid testing, and you can actually simulate any wind turbine loads as you want. And if you do, for example, if you want to introduce the loads due to the fault condition, for example, the blade cannot be pitched, and then introduce these transient loads. It's very difficult if you do this at the model scale, because the dimension will be very small. But you are free to do this actually at a numerical scale, so that you can impose these loads numerically and then apply them on the physical structure when you're doing the model test. I just mentioned that, I forgot to mention that, of course, the test is carried out at a model scale, but these loads are actually estimated at the force scale and then downscaled by fluid scaling law, so that you apply at the model scale value in the model test. And then, of course, you have to do this real time so that it evolves with the same time to have the coupling effect. And here is just showing some details. Actually, this red line, you do not see it very clearly, but they are the cables connected to the end of the basin, and they are controlled by the motor. And then, of course, you have this delays also when you apply the load. So you have to compensate that delays when you apply the desired loads on the turbine. And here we just also give some examples from the test. Another issue is that we also look at actually the loads in the floater. And in the test, we cut the column so that we mount a load cell so that it can be measured, the load at the cut. And then we also compare with the numerical model where you have to separate the floater into two bodies. So you estimate the wave excitation loads at the two bodies, and then you also do the numerical dynamic analysis. You can get the cross-sectional loads at that point. And here we compare with the measurement and the time domain simulations. And of course, in this case, we use the measured wind and measured wave elevation as input for the simulation. So then you can get exactly the same time series response. And this is also done combined with hybrid testing. And I just want to mention that this is a testing carried out in ocean basin. And then in the University of Milano in Italy, they have a wind tunnel. Typically, they use testing for fixed wind turbine or wind turbine profile. And then they are also now trying to introduce a movable foundation so that you can simulate also the motion of the floating wind turbine, and then also doing a test to look at the loads on the blades when the foundation is moving. Yes, so yeah, basically I'm done. So I just recap a little bit about what I presented today. Some overview of bottom fixed and floating wind turbines, basic design consideration, and then also give you some about detail about the aerodynamics and hydrodynamics of horizontal axis wind turbine and vertical axis wind turbine. And then also I give some of the highlights of the recent work we have done at NTNU. So you have also a brief list of references, and if you want, you can look at more in details. Yes, thank you very much. And so if you have any other final questions, so you can just ask. They can be related to any part of my presentation. Yes?
Thank you. Is it working?
Yeah.
No, it's working. I had a question related to the first part, actually the first slides. You showed at the beginning how the size of the wind turbine increased over the years, starting from 2 megawatt, and currently in 2016 we already have 8 megawatt turbine, which is like really big, like a whole power plant. And my question is, how do you see the development in the coming years? Is there any limitations on the size? Can we have, I don't know, 10, 20 megawatts turbines? What do you think?
Yeah, myself, I'm not an expert on wind blades. What I understand is that the turbine size are mainly limited by manufacturing issues. So if you have a large turbine size, you have a very long blade. And for offshore, of course, there are the issues about transport and installation, particularly for onshore application. But for offshore, I think there will be no problem. If you have a manufacturer close to shore, then you can bring the turbine blades to the site with boat, and then do installation on site. So it will be typically limited by the blade itself in terms of the strength and the manufacturer issues. So that is what I understand. So There's also research working on 10 megawatts and 15 megawatts of blades. So yeah. It will increase, but I don't know how large it will reach. Yes.
Okay. Thank you.
Mm-hmm. Any other questions?
So if there are no more questions, I'd like to thank Professor Zen once again. And thank you for coming. Have a nice lunch.